Hello, everyone. Welcome to the explanation of the first part of the chapter Light, Reflection, and Refraction. So, in this part, I'll be covering what is reflection of light and different types of mirrors, their image formation, their use cases, and also will deal with numerical problems. So, without wasting any more time, let's get started. So, the first thing that we will see here is the reflection of light, which you have already learned in your lower classes. So let's just quickly revise what is reflection of light and what are the things that we need to remember. As you must have learned from your lower classes, reflection of light simply means bouncing back of light when it hits any smooth surface like a mirror. So in this case, let's assume that we have a mirror whose reflecting surface is pointing upwards. Let's also name it as M1. Now, let's assume that a light ray hits the mirror at a particular angle. Let's name it as PQ. Now, this light ray PQ can be called as the incident ray. After hitting the mirror at point Q, the light ray is reflected back and we can call it as reflected ray. So let's name it as, say, QR. So ray QR is your reflected ray, whereas ray PQ is your incident ray. This line that you see here is called as a normal. A normal is an imaginary line drawn from the point of incidence perpendicular to the reflecting surface. So as you can see, we have drawn it perpendicular to the mirror MM dash, and it actually forms angle with both incident ray and the reflected ray. The angle formed by the normal with the incident ray, this angle is called as angle of incidence given by letter I, whereas the angle formed by reflected ray with the normal is given by letter R, and it is called as angle of reflection. So this was the basic of what happens in the reflection, which you already know. You should also know the laws of reflection. Laws of reflection states that the angle of incidence and angle of reflection are equal in a reflection. The second law of reflection states that the incident ray, the reflected ray, and the normal to the point of incident, they all lie in the same plane. So these are the two laws of reflection, again, which you have already studied in your lower classes. Let's move on to the image formation by plane mirror. In case of plane mirror, you will have to remember the four different characteristics of the image formed by a plane mirror. A plane mirror always forms a virtual and erect image. Now, in short, what is a virtual image? A virtual image is the one which is formed at a point where light rays appear to meet or intersect. Remember, they are not actually meeting at that particular point, which means if you place a screen at a point where the light rays are appearing to meet, for example, in this diagram I've shown here, that the light rays appear to meet behind the mirror. If I place a screen here, I will not be able to get this image on the screen, as there are no light rays meeting at this particular point. So plane mirror always forms a virtual image, and virtual images are always erect. Second characteristic of the image formed by plane mirror is the image is same size as that of the object, which means the magnification produced by plane mirror is always 1 and plus 1 specifically because it is a virtual and erect image. Third characteristic is the image formed by plane mirrors are laterally inverted. In simple words, they are horizontally flipped. So that's why some letters like say letter C or letter P, which I've showed here, they look flipped in the mirror when we hold a book or those letters in front of the mirror. You must have also noticed that if you raise your left hand, the image actually raises the right hand, and so on. So this is called as lateral inversion. The last thing or the last characteristic that you need to remember about the image formation by plane mirror is the distance. The distance at which the image formed behind the plane mirror is equal to the distance of the object from the plane mirror. Say for example, if the image is formed at 10 centimeters behind the mirror, it also means that the object is placed at 10 centimeters in front of the mirror. So these are the 4 characteristics. Just to repeat, plane mirror always forms virtual and erect image. It always forms an image which is same size as that of the object. It always forms laterally inverted images, and it forms image at the same distance from the mirror as that of the object. So these are the 4 different characteristics of the image formed by the plane mirror. The next part we are going to see is spherical mirrors. Now, there are two types of spherical mirrors we are going to learn here. One is the concave mirror, and the other one is the convex mirror. Spherical mirrors are usually made by using hollow spheres of glass. As I've shown here, you can see that if I cut the hollow sphere, the part which I've shown in dotted line, if I cut it, I'll get a mirror whose reflecting surface is sort of curved inwards, and this type of mirror is called as a concave mirror, whose reflecting surface is curved inwards, as I've shown here. Similarly, we can also make a convex mirror if we make a mirror whose reflecting surface is curved outwards by using a sphere of a glass. So these are the 2 types of mirrors that we'll be learning here, concave and convex. Alright, let's try to understand the different points that we need to remember with respect to these 2 mirrors, or in other words, anatomy of these mirrors. So I have marked 2 mirrors here with the dotted line representing the spheres from which these mirrors have been made. The one on the top is a concave mirror. As you can see, the reflecting surface is curved inwards, whereas the bottom one is a convex mirror where the reflecting surface is curved outwards. Now, the center of the reflecting surface of this mirror is called as pole of the mirror, given by letter P. Letter P is pole of the mirror. It also applies to the convex mirror. The center of the reflecting surface is called pole of the mirror. The center of the sphere from which the mirror is made is called center of curvature, given by letter C. I repeat, the center of the sphere from which the mirror is made is given by letter C, and it is called as center of curvature, as I have marked for both the mirrors here. Center of curvature is letter C. An imaginary line joining these points can be called as the principal axis. So I'll draw a line here. An imaginary line which joins these 2 points can be called as a principal axis, as I have shown here. If you look carefully, the distance between the point P and point C is also the radius of the sphere from which the mirror is made. So it's given by letter R. So R is radius of curvature. Radius of curvature. It also applies to the concave mirror. Distance between point C and point P is radius of curvature given by R. Concave mirror is a converging mirror, whereas convex mirror is a diverging mirror. So let me write it. Concave is converging, whereas convex is diverging. So if I pass light rays parallel to the principal axis of a concave mirror, let's say we are passing light rays parallel to the principal axis like this, and they are traveling in this direction. After reflection, they will converge at a point on the principal axis, and this point where they converge after reflection or meet after reflection is called as focus or principal focus, given by capital letter F. If I pass light rays parallel to the principal axis of a convex mirror, they will diverge. But if I trace them backwards, they will appear to diverge from a single point. And the point from where they appear to diverge is called as the focus of a convex mirror. So the difference is a concave mirror has a real focus, whereas a convex mirror has a virtual focus. So if I place the object at infinity of concave or convex mirror, both these mirrors are going to form a very tiny image at the focus. The difference is the image formed by concave mirror is a real image because the light rays are actually intersecting at this particular point, whereas the image formed by convex mirror is a virtual image because the light rays appear to diverge from this point. So concave mirror has a virtual focus, concave mirror has a real focus and convex mirror has a virtual focus. A real image is always inverted, unlike the virtual images. So the image formed by concave mirror in this case will be inverted. And since the light rays are actually meeting there at that particular point, the image can be also produced on a screen. So if I place a screen at focus here in this case, when the object is at infinity, I'll be able to produce that image on the screen. So these are the two basic differences between real images and virtual images. Now, coming back to the different points here. The distance between F and P, that is focus and the pole, is called as focal length. So if I take distance between these 2 points, I'll call it as F, focal length given by small f. Small f is focal length. And what is focal length? It is distance between the point P and point F. So again here, in case of convex mirror also, same logic applies. Distance between point P and point F. This distance is focal length given by small f. Always remember, distance C and P is double that of distance PF. Distance CP is double that of distance PF. We also know that distance CP is radius of curvature given by R, and distance PF is focal length given by small f. So we can establish a relationship between radius of curvature and focal length. That would be R is equal to 2f radius of curvature is twice the focal length. The next part of this chapter is formation of image by spherical mirrors. So for now, we'll focus on concave mirror and see how it forms an image. Before we move on to actual image formation diagrams, we need to remember a few rules which we can use to draw these diagrams. So let's start. The first rule says that if a light ray is traveling parallel to principal axis, then after reflection, it will pass through focus. Then we show the arrows traveling parallel to principal axis after reflection passes through focus. The second rule is kind of opposite to the first one, we can say. If a light ray is passing through focus, then after reflection, it will travel parallel to the principal axis. That's our second rule. If a light ray is traveling through focus, then after reflection, it will travel parallel to the principal axis. The third rule says that if a light ray is passing through center of curvature, then it will reflect back in the same direction. Whereas the fourth rule says that if a light ray hits the pole of the mirror, now if a light ray hits the pole of the mirror, the principal axis itself becomes the normal and we get angle of incidence here. So this ray will reflect by maintaining the same angle with the principal axis. So this will be your angle of reflection. So these are the four rules. Out of these four rules, we can use any two rules to show the image formation by concave mirror. So now let's actually see how we can draw the ray diagrams to find the image formation by concave mirror. So we'll start off by drawing a principal axis somewhere around 10 centimeters should be enough, but you can always extend this line whenever you need. Next part is I have to mark 3 points, and all these 3 points should be at equal distance from each other. So let me mark 3 points. You can take 2 centimeters or 3 centimeters depending upon your choice, but they should be equal distance from each other. Let me mark 1 point over here, 1 point here, and 1 point here. Now I've taken 3 centimeters as a distance. You can take 2 centimeters depending upon the size of your book. Now let's name them. This is point P. This is your point F, the focus, and this is the center of curvature, that is point C. Now we have to draw the mirror. For that, you can use your compass. Place the pointer of the compass at point C. Extend your compass till the point P, and you're going to mark an arc at point P. Something like this. I'll repeat. I'll redo that. You're going to place the compass at point C, extend the compass up to point P, and mark an arc. So this gives you your concave mirror, and we can show the reflecting side of the mirror and then also name the mirror. Now we are going to place the object. Generally, the position of the object is given in the question. So here I have written object is placed beyond center of curvature. So let's place the object beyond C, after C on the principal axis. So for representing the object, we'll draw an arrow after C, and we'll name it as A, B. The height of the object can be around 1.5 to 2 centimeters. Again, depending upon the size of the mirror, see to it that it doesn't go beyond the size of the mirror. Now we have to follow any of the 2 rules out of the 4 rules that we have studied and get the image formation. So let's use the first rule. The first rule says that if a light ray is traveling parallel to principal axis, after reflection it will pass through focus. So you have to start your light ray from the top of the object and hit the mirror. Then from the point where it has hit the mirror, you have to pass this light ray from the focus, as I've done here. Let me show the arrows to show the direction in which the ray is traveling. So this is my first rule. Let's use the second rule and see where we get the intersection, or if at all we get the intersection. The second rule says that if a light ray is traveling through focus before reflection, that is. So again, I'm going to start the light ray from the point where the object starts, or from the top of the object rather I should say, and then pass it through the focus. And once it hits the mirror, I will then make it travel parallel to the principal axis. So I have got my 2 light rays and I have also got the intersection. Now, intersection is the point where your image is formed. So you can see my light rays are intersecting here between points C and F. So that is the point I am supposed to draw an arrow. Since the light rays are actually intersecting here, we can say that this image is a real image, and that's why it is also inverted. So let me also name the image. We'll name it as A1, B1. So that is my complete diagram. You can also mention the nature, size and position of the image. So for nature, I will say it is real and inverted. For position, I will say between C and F. And for size, I'll say diminished. Diminished because it is smaller than that of the object. If you're unsure, you can just take your scale and basically measure the height of the object and the image and check whether they are same size or smaller or larger. If it is larger, if the image is larger, we'll say enlarged. So this type of image, as you can see here, which is formed by actual intersection of light rays, is called as real and inverted image, and this image can be produced on a screen. Let's have a look at one more diagram here. Now in this particular diagram for concave mirror, we are going to see formation of image when we place the object between F and P. So I have done the initial layout. I have placed 3 points at equal distance from each other, and I have also drawn the mirror. I have placed the object between F and P, as you can see here. Okay, so let's begin drawing this diagram by using the first rule. The first rule says that if I place, if a light ray passes parallel to the principal axis after refraction, it will travel through focus. So I'll start from the top of my object as we had done the last diagram, and I'll draw a straight line or parallel to the principal axis hitting the mirror. Once it hits the mirror, as we have done last time, we have to simply pass it through the focus. So let me pass it through the focus. So we get a light ray something like this. Let me show the arrows. Now, we have to draw one more light ray and see how it passes, but since our object is placed in front of F, we'll use the third rule instead of the second rule. That is, if a light ray passes through center of curvature, it reflects back in the same direction. So I'll draw a straight line passing through C from the top of the object. Now if we do this, you can see that we are getting diverging light rays here. The light rays are traveling away from each other. So whenever we get diverging light rays, we try to trace them backwards and see if they appear to meet behind the mirror. So we'll take the ruler and trace back the same light ray with dotted lines. Let me just undo that. So we'll take the ruler and trace back the same light ray behind the mirror with dotted lines. We don't know where they'll exactly appear to meet, so we'll continue for a little distance. Then we are going to do the same with the first light ray as well. We are just going to place the ruler correctly and we are going to extend with dotted lines. And there you go. You can see the light rays appear to meet behind the mirror or appear to diverge from a point behind the mirror. Now this is the point where your image is formed. So since this is a virtual intersection, the image formed here will be virtual and erect. So it will be an erect image, something like this. So we'll name the object as well as the image. We can name the object as AB. We'll name the image as A1, B1. So this is another diagram which shows you a virtual image. Now you can see the difference that we got between a real image and virtual image. Real images are formed in front of the mirror in cases of mirror, whereas virtual image is formed behind the mirror. Real images are formed by actual intersection of light rays. Virtual images are formed at a point where light rays appear to meet or converge. Real image can be produced on a screen and virtual image cannot be produced on a screen. These are the three major differences between real image and virtual image. This part explains the image formation by convex mirror. Let's first understand the rules that we need to follow. Now remember, convex mirror is a diverging mirror, so the light rays traveling parallel to principal axis of a convex mirror will diverge or appear to diverge from its focus, as we have seen previously. So let's understand the rules. The first rule says that if a light ray is traveling parallel to principal axis, like so, then it will diverge or appear to diverge through focus. So it will appear as if the light ray is diverging through focus. Let me get that correct here. So it will diverge in this direction, but it will appear as if it is diverging through focus. So that is the first rule. The second rule is kind of opposite to first one, I can say. If a light ray appears to pass through focus, something like this, then after reflection it will travel parallel to the principal axis. So the second rule says if a light ray appears to pass through focus, after reflection it will travel parallel to the principal axis. So they are quite opposite to each other. The third rule is quite simple. If a light ray appears to pass through center of curvature, something like this. If a light ray appears to pass through center of curvature, then it will reflect back in the same direction. And the fourth rule is like the fourth rule that we saw in the concave mirror, that if a light ray hits the pole of the mirror, basically it is going to create an angle with the principal axis, and it is going to reflect with this by maintaining the same angle with the principal axis. Now, in the convex mirror, there are only two diagrams. One is when the object is placed at infinity, and we have already seen that if the object is placed at infinity or light rays are traveling parallel to principal axis, the image will be formed at focus, which will be tiny, virtual and erect, highly diminished image. But if the object is placed anywhere between infinity and pole, then the image will be formed between P and F. So let's understand how to draw this diagram when the object is placed anywhere between infinity and pole in front of a convex mirror. So let's begin and understand how this image formation happens. So here in this particular question, we are going to place the object anywhere between infinity and pole of the mirror, which means anywhere on the principal axis in front of the mirror on the left hand side. So maybe I'll place the object somewhere over here in front of the principal axis. Now we have to simply follow any of the two rules and get the image formation. So the first rule, as we have seen, says that if a light ray is traveling parallel to principal axis, after reflection, it appears to diverge through focus. So this is our first rule, that if a light ray is traveling parallel to principal axis, after reflection it appears to diverge through focus. Now let's draw the second rule, or I'll use the third rule in this particular case, that if a light ray appears to pass through center of curvature or is heading in the direction of center of curvature of the convex mirror, then it will reflect back in the same direction. So I'll draw this. Now, since there is no intersection happening after reflection in front of the mirror, we'll just trace it backwards. And you can see that these light rays are actually intersecting behind the mirror, or appear to intersect behind the mirror. And this is the position where your image will be formed. So let me draw the image wherever there is intersection. So let me name the object as AB. Let me name the image as A dash or A1B1. So remember, convex mirror will always form a virtual, erect and diminished image, no matter what the position of that particular object is. This is because it is a diverging mirror. And when we see the uses of convex mirror, we'll understand why this particular property of convex mirror is useful to us in many cases. So if you've noticed while drawing the diagrams for the concave and convex mirror, you must have seen that if a light ray is passing through the center of curvature of the concave mirror, or say appears to pass through the center of curvature of a convex mirror, it is reflected back in the same direction. So what could be the reason for this? The simple reason for this is the light ray is hitting perpendicular to that particular point on the mirror, or you can say the light ray is hitting along the normal to the point on that mirror. So remember that whenever a light ray hits perpendicular to any point of the mirror, irrespective of the shape of the mirror, the light ray will reflect back in the same direction. Now let's talk about the uses of concave and convex mirror. We'll start off with concave mirror. Concave mirror is used by the dentist to get the enlarged image of the tooth which has been damaged probably, or has the cavity. Concave mirror can be also used as a shaving mirror. The reason for both these use cases is the same, that is, when you place the object between F and P, between the focus and the pole, you will get highly enlarged image of this object behind the mirror. So the image will be virtual and erect and highly enlarged image. So this allows the dentist to see the magnified image of the damaged tooth. The other uses of concave mirror may include it can be used in solar cooker, for example, to create intense heating inside the solar cooker. Concave mirror is also used to reflect and produce a parallel beam of light in car headlights as a reflector. So in this case, the concave mirror is placed behind the bulb, and the bulb is usually placed at the focus of the concave mirror. So what happens because of this is when the bulb is lit, the light rays coming from this bulb are reflected in such a way that it produces a parallel beam of light which can travel or cover a longer distance. Convex mirror, on the other hand, can be used as a rear view mirror in the cars. The main reason for this is it forms virtual, erect and diminished image irrespective of the position of the object. Wherever the object is, it is always going to produce a smaller and virtual erect image. Convex mirror is also bulged outwards, so it covers wider area. So that is one more benefit of using convex mirror as a rear view mirror. Convex mirror can be also used on junctions to cover the blind spots that we normally have on the roads. Convex mirror is also used as a reflector in street lights. Now again, just like the concave mirror in car headlights, this reflector is placed behind the bulb, so when the light rays reflect from the convex mirror, they are diverged away from each other, giving you a wider coverage. That means more area will be illuminated by the light. So these are some of the important uses of convex and concave mirrors. Now in this part, we are going to understand how to solve the numerical problems related to mirrors. For this, we have to use something called as the mirror formula. So the mirror formula is given as 1 upon V plus 1 upon U is equal to 1 upon F. Now here U is the object distance. In other words, it is the distance of the object from the pole of the mirror. V is image distance, which is the distance of the image from the pole of the mirror, and F is focal length, which we already know is a distance between point P and point F, that is focus. While solving these problems, it is very important to use a sign convention. Unless we use the sign convention, we won't be able to get the correct results for these problems. So, by applying the sign convention, some values are taken negative and some values are taken positive. So, we'll see how to use this new Cartesian sign convention, and then we'll see how to solve one problem. This is the Cartesian coordinate system that we use for solving problems or assigning signs to different values. To start off with, you have to assume that your mirror, whether it is concave or convex mirror, it is positioned at 0, 0, or in other words, the pole of that mirror is positioned at 0, 0, something like this. All the horizontal measurements that we are going to do, all those measurements will be done with respect to the pole. For example, if we are measuring horizontally on the right hand side of the pole, we'll take those values as positive. If we are measuring anything on the left hand side in front of the pole, we'll take those values as negative. If we are measuring some height which is vertically upwards, we'll take those values as positive. And if we are measuring something vertically downwards, we'll take those values as negative. So let's take some examples and try to understand which values are taken positive and which values are taken negative. For simplicity and for our understanding, we'll always believe that the object is placed on the left hand side of the mirror or in front of the mirror. So this distance between the object and the pole of the mirror is U, or the object distance. And since we are measuring this distance towards the left hand side from the pole, we will always take this value as negative. So U is always taken as negative. This here is the height of the object given by H or HO, which is measured vertically upwards, and hence we can take this value as positive or always positive. So height of the object is always positive. Height of the image, whether it is to be taken positive or negative, depends on the nature of the image. If the image is virtual and erect, in this case, for example, the image is virtual and erect, and as we know, these images are formed behind the mirror. So in this case, if the image is virtual and erect, the height of the image, which is given by HI, will be taken as positive. But if the image is formed in front of the mirror and if it is inverted, in this case we are going to measure the height vertically downwards. So we'll take this height of the image as negative. So if the image is virtual and erect, height is taken as positive, and if the image is real and inverted, the height is taken as negative. The same thing really applies to the value of V. Now V is the distance of the image from the pole of the mirror. For example, this is V, and even this distance can be called as V depending upon where the image is formed. If the image is formed behind the mirror, which is virtual and erect image in case of mirrors, we'll take V as positive. But if the image is formed in front of the mirror, we'll take V as negative. Focal length of concave mirror is taken as negative, and focal length of convex mirror is taken as positive depending on the location of the focus. Since the focus of concave mirror is located in front of the mirror, focal length of the concave mirror becomes negative, whereas since the focus of convex mirror is located behind it, the focal length becomes positive. One more concept which we have to deal with here is the concept of magnification. Now, magnification is, by definition, we can define it as a ratio between height of the image to the height of the object. So we can write it as M is equal to height of the image, which can be written as HI, divided by height of the object, which is HO. Since it is a ratio, it will only have a value and a sign depending on the nature of the image. Magnification is also given by negative V upon U. So we can also continue this formula as minus V upon U, which is negative value of image distance upon object distance. So let's understand the meaning of the value of magnification. Let me just erase this. Magnification, as I said, can be positive or negative depending upon whether the image is virtual, erect, or real and inverted. So you will get negative magnification if the value is if the image is real and inverted, and positive magnification if the image is virtual and erect. Suppose the magnification produced by a mirror is +2, or let's say another mirror produces a magnification of -2. Now you have to look at magnification in two parts. If the value of magnification is greater than 1, the image is enlarged, which you can see here in the first case. But normally when we get number line in our head, we'll say that -2 is less than 0, which is smaller than 1. So the image is not enlarged, but that is not the case here. So I would suggest is look at the value of magnification in two parts. Just look at the sign first. If the sign is positive, then the image is virtual and erect. And if the sign is negative, the image is real and inverted. Then completely ignore the sign and look at the value. If this value is greater than 1, then the image is enlarged. Now in this case, in both the cases here, if the value is greater than 1, which is 2, so this particular value is telling me that the image is 2 times larger than the object. But in the first case, it is 2 times larger and virtual and erect. In the second case, it is 2 times larger and real and inverted image. So any magnification value, you are going to look in two parts. We can take one more example. Suppose the magnification produced by a mirror is -1 or +1. If it is -1, I'll say real, inverted, same size. If it is +1, I'll say virtual, erect, and same size. So if the magnification value is 1, it means that the image is same size as that of the object. If the value of magnification is less than 1, maybe 0.7, positive, negative, again doesn't matter, because positive and negative will just tell you the nature of the image. If the value of magnification is less than 1, like 0.5 or 0.7, then the image is diminished. Now, it can be positive 0.7 or it can be negative 0.7, doesn't matter. Positive means virtual erect, negative means real and inverted image. So that is how we read magnification. Also, This formula can be used to find the height of the image, as we'll see in a problem. Alright, so let's try and understand how to solve this numerical for concave mirror. But you can apply the same method for convex mirror as well. Let's first decode this particular problem line by line and also draw a rough diagram maybe to understand what is the situation here, and based on that we are going to use the different signs that we have learned as per the sign convention and the mirror formula obviously to solve this problem. So the problem says a 6 centimeter tall object is placed perpendicular to the principal axis of a concave mirror. So let's decode the first line. We have a concave mirror, so what we have understood, and there is an object of height 6 centimeters. So this is the pole of the mirror, this is the focal length of the mirror, and this is the center of curvature. This pole, focus, and the center of curvature, sorry. So an object of height 6 centimeters is placed on the principal axis of focal length 30 centimeters. So which means this distance between P and F is 30 centimeters. I'll come to the height of the object a bit later. So this distance, small f, is 30, and since the focus is on the left hand side, we'll take it as negative 30 centimeters as per the sign convention. The distance of the object from the mirror is 45 centimeters. If the distance between P and F is 30 centimeters, then distance between P and C, this whole distance will be 60 centimeters, which is our radius of curvature. And the problem is saying that the object is placed at 45 centimeters from that of the mirror, which means the object is placed somewhere between C and F. It's not very important to know this while solving the problem, but we are just trying to decode everything possible by reading the problem. That will make our job easier. Also, we have been told what is the height of the object. So this particular height is given, which is height of the object, and we have been told that it is 6 centimeters. Now height of the object is always taken positive, so it is plus 6 centimeters. We need to find position, nature, and size of the image. So we'll have to find what is V, that will give us the position of the image formed. Nature we'll come to know once we know the position of the image and once we also find the size of the image formed. So once we find both these, we'll figure out how to know the nature of the image as well. So let's start by putting in the mirror formula. The mirror formula is 1 upon V plus 1 upon U is equal to 1 upon F. Now let's shuffle around. We need to find the value of V. So you can either first substitute the values here, or maybe you can first readjust the formula so that we get the correct left hand. So we can readjust the formula so that we can find V very easily. So I would say 1 upon V is equal to 1 upon F minus 1 upon U. So what I've done simply here is I have shifted U, 1 upon U, to other side. That's why the sign has changed from plus 1 upon U to minus 1 upon U. Now I will substitute the values. So value of F is negative 30. So 1 upon negative 30 minus 1 upon U, which I forgot to write here, by the way. It is given in the problem that U, object, is placed at 45 centimeters. So which means this particular distance is u, which is 45 centimeters, and u is always negative. So it is negative 45 centimeters. Now, the LCM of 30 and 45 would be 90. LCM is always positive irrespective of what signs we have. I'll take negative sign of 30 as it is in the numerator, and I'll write 30 multiplied by 3 is 90. Now here, because there are two negative signs, this whole sort of fraction will become positive, so I'll have to write plus, and 45 into 2 is 90. So therefore, I'll get 1 upon V as negative 1 upon 90. I'll reciprocal on both the sides. Therefore, right below, therefore, V is equal to negative 90 centimeters. So this is the position of the image. The image is formed at 90 centimeters in front of the mirror on the left hand side. Because the value of V is negative, we can know that it is formed on the left hand side, which also tells us that the image, the nature of the image is real and inverted. Real and inverted. Because in mirrors, real and inverted images are formed in front of the mirror, whereas virtual and erect images are formed behind the mirror. We have to also find the height of the image formed. Again, once we find the height, we'll also be able to confirm the size, the nature of the image formed here. So to find the height of the image formed, I'm going to use part of the magnification formula, that is height of the image to the height of the object is equal to negative V upon U. So height of the image we have to find. Height of the object is given as 6 centimeters. Value of V we have found as negative 90. Now there is already one negative in the formula, so I'll write minus of minus 90 divided by U is negative 45. Now let's cancel negative with negative. Let's also cancel 45 with 90. 45 ones are 45, 45 twos are 90. And now if I simply cross multiply, my answer would be height of the image is equal to 6 multiplied by 2, which is 12, and there is a negative sign, so negative 12 centimeters. So negative sign for the height of the image again confirms that the image is real and inverted. We should also compare the height of the object with the image. Height of the object was given as 6 centimeters and the height of the image is 12 centimeters. Mind you, the negative sign will only tell you the nature of the image. You have to still consider negative 12 as 12 centimeters. So this is double the size as compared to the object. That means the image is enlarged. So that is how you solve these problems for finding the position, nature and size of the image formed by spherical mirrors. So that completes the part 1 of this particular chapter. If you have any difficulties in understanding any of the concepts covered in this particular part of the chapter, please leave a comment below and I'll try and make another video covering that part of the chapter. If you've liked the video, then please subscribe to the channel and don't forget to watch the part 2 of this particular chapter. I'll leave a link to that particular part in the description below. Thank you for watching.